right, well, good afternoon, everyone. Thanks for coming. I know it's right after lunch, so I got to keep this lively to keep you awake. My name is Eric Diaz. I'm with Agilent Technologies. I'm based in Santa Rosa, California. And in this presentation, I'll be discussing using signal generation techniques to exercise and test Counter-IED defeat systems. So these jamming systems are used, of course, to deal with terrible scourge that unfortunately is a very real part of modern warfare. You know, the improvised explosive devices, which take a big toll on human life. And so there's been a lot of effort in recent years to try to come up with systems to jam and defeat these IEDs. All right, so of course, you know, the end goal is we're trying to reduce the toll on both military and civilian casualties. So in this presentation, I'll describe using a signal generator along with software done with MATLAB to try to create realistic signal scenarios to evaluate the EW system and exercise it in realistic ways so that when it gets deployed and fielded, there's high confidence it'll work in the way it's intended to do. Here's a very rough example of the kind of geometry and environment that we might face. So as a vehicle is driving down a road, of course you have to contend with various cellular towers that might be there, broadcast stations, radio and TV stations. There might be various push-to-talk radios in the environment. And these signals could be at a number of different frequencies. It could be at any different power level. It could be coming from any direction. So it's a very challenging environment. Generally speaking, most of these signals that might be used perhaps to detonate an IED would be kind of in the 0 to 6 gigahertz frequency range. It's much, much less common for, say, microwave signals to be used for these purposes. So the idea is to try to look in all directions. Generally these would be omnidirectional kind of systems that you might use to jam, since the signal could come from any direction. And you're obviously trying to do the best job you can to evaluate as many signals as possible and act very quickly to be effective. Now, there are a number of different categories of signals we might encounter. Certainly one very typical category is what we call digital signals. Generally, this would be things keyed from a cellular phone, so it could be, say, a GSM or WCDMA kind of signal that we might be dealing with. The good news is that those operate in well-defined frequencies. So for any cellular service provider in a certain region, they would know exactly the frequency plan that's being used in that area, what frequencies these potentially harmful signals might exist at. So generally our intelligence services, of course, would get that frequency plan information and use that to look in those specific areas. So again, using GSM as a real general example, it's a TDMA type system, so there's time slots. So our jamming system might take a couple of different approaches. One might be to maybe a little more brute force approach and just block the entire broadcast channel. So that's effective, but that takes more power for a greater period of time. Or it might try to be a little more selective and block certain time slots or control channels to prevent specific signals from being transmitted. Again, it's really kind of a trade-off between how much power you have available and what other areas of the spectrum you need to look at. Another very broad category of signals that are, again, potentially very dangerous would be analog signals. And these could be from, say, a push-to-talk FM radio or a garage door opener that might have very, very simple types of modulation, like on-off keying that could, in some code could trigger an explosion. Here, for example, we start out by looking at the full 6 gigahertz frequency range. And by zooming in the lower portion up to, say, 660 megahertz, you can see there's a very large number of fairly low-level signals. And so you have to evaluate these very quickly to determine which ones might be potentially harmful signals. Here, for example, say we had a signal around 300 megahertz where it gets keyed on, it's a squelch tone, and you can see that when the signal comes on, there's very narrow band modulation. It's like less than 100 hertz modulation, and it's rising up in about 50 milliseconds. So that gives you an example of the kind of time frame you've got in order to operate on these signals. So you have to be able to, as you're searching around, find the signal, detect it, analyze it, and act on it before it has a chance to come up to power and possibly cause a detonation. So again, very high processing speeds becomes very critical. Now for EW engineers who are designing these systems, probability of intercept is a very key parameter we have to be concerned with. And so this involves looking at signals in terms of time and space and frequency. So you have to catch a signal at the right time. You have to be in the right location, or within the range where you can detect this signal, and you have to be tuned to the right frequency. So it's a very multi-dimensional problem, again, which requires looking very quickly over frequency, in a rapid time frame, and looking in all directions. All right, so this would be a typical spectrum. Again, looking over the 6 gigahertz range, you can see that there's a lot of signals we have to evaluate. And so generally there would be a search schedule you might do where you try to look intelligently rather than look at all signals in sequence. You might look in certain areas that are higher priority. There may be intelligence information that would suggest that certain frequencies are more suspect, and so we're going to want to look at those first. You can also see there's a wide range of amplitudes we have to evaluate, and again, the markers there indicate, give us some idea that, maybe we've got 60 dB of range we need to be concerned with. So we have to have dynamic range to look at those different kinds of signals. A typical receiver architecture might involve multiple receivers, so you might have a scanning receiver, a very fast one that can scan quickly over a wide range. And when certain signals of interest are found, they might be handed off to a handoff receiver that then looks in more detail at specific frequencies. All right? And again, if there's intelligence information that suggests that certain frequencies are more suspect, you might be monitoring those all along to look for potentially harmful signals. All right, so there's a scanning aspect as well as the monitoring aspect. So again, for the EW engineer who's designing the system, there's three main or broad categories we have to be concerned with. We have power and amplitude issues, timing issues, and modulation issues. Each one of those has certain implications. So, for example, with power issues, that has an impact on, if we want to simulate the harmful signals that may be either close to the IED or far away from the IED, that impacts the range over which the jammer is affected, and also the affected radiated power of the detonation signal. All right, that in terms, or that therefore has implications on the system performance that we're looking for. So that means the jamming system has to have enough dynamic range and sensitivity and interference, or ability not to have distortion, and have enough jamming to signal ratio to be effective against that particular detonation signal. And then finally, that has implications on the instruments we want to use to simulate the signal. So we want to make sure our signal generation system has enough power and switching speed so we can simulate multiple signals, have enough bandwidth, and modulation types. Again, we can simulate the do a realistic simulation of the detonation signal. In terms of timing, again, the faster our system can tune to different frequencies, the greater the number of potential harmful emitters we can simulate, and we can multiplex very quickly between these signals to do a more realistic environment. Again, the implications for the EW system then are having an accurate and sufficient search schedule that allows us to look at all these different frequencies very quickly and have very high probability of intercept and have enough jamming to signal ratio. Once you detect the signal, how do you jam it to prevent the explosion from going off? Again, the implications for the test system then are you have to have enough switching speed, sequencing memory to again hop between all the various frequencies and have enough bandwidth. And then finally, with modulation, again, it could be GSM modulation, WCDMA, or some other cellular type of signal we're looking for and trying to simulate, or it could be a very simple analog modulation, just on-off keying. So we want to be able to create all those kinds of signals in our simulation environment, again, to make sure that the EW system is working as it needs to. All right, so on the hardware side, a typical signal generator might be something like this MXG, which covers the 6 gigahertz range, has fairly fast frequency switching, so it can go from one frequency to another in a millisecond. It has wide arbitrary waveform generator bandwidth, so you can simulate 160 megahertz of bandwidth at the same time. Wide power range to go from very high power levels to very low, so we can simulate maybe a detonation signal that's very far away. Again, various sweep modes and list modes, so you can set up a list of frequencies where you can very quickly hop from one frequency to another in order to simulate multiple signals. All right, so in looking at the spectrum again, up to 6 gigahertz, we see lots of signals. In terms of amplitude, you can see there's a very wide range of amplitudes we might have to deal with. Typically, if we exercise a jamming receiver, we might look at anywhere from 100 to 160 megahertz chunks of bandwidth at a time. And so in doing that, we might want to look at signals perhaps as low as minus 110 dBm in order to simulate those low-level dangerous signals. Now, here again, zooming in from the full span, we might go down to a narrow span, looking at the GSM band in particular. Some of those signals can be very noise-like. There's digital modulation on there, which we can simulate with noise. And so you want to be able to, again, create those kinds of signals to exercise the EW receiver. So as we create these signals, really one of the basic questions the EW engineer needs to do is ask himself, what is it you're trying to test? All right, what are the goals of the testing? So if you're primarily concerned with specific frequencies, you might just have a list of those frequencies in the signal generator and test one at a time, test individually to see how it behaves. Or you might want to create multiple signals at the same time. All right, so perhaps using a baseband generator, you can create a wider band representation of the environment and have multiple signals and see how the receiver behaves against that. In some cases, you might want to actually use a recording of actual environmental signals from the area. So that's probably the most realistic type of test. But again, it adds more complexity. So in general, the more realistic and the more complete the test, the complexity of the test system grows with that to exercise that jamming receiver. Okay, remember the third broad category we have to be concerned with is the modulation capabilities. Again, we want to be able to simulate various cellular formats, for example, or AM and FM type signals or pulse signals. Might want to use arbitrary noise, so AWGN type signals. Or we might want to be very flexible and create a very custom waveform to simulate the kinds of detonation signals that might exist. And this can be done in a vector signal generator fairly easily using the baseband generator. You create a waveform of the signals you want, download that into memory. That's separated out into the I and Q branches of the baseband generator. So we would then filter those I and Q samples, go from a D to A converter to create an analog signal, filter it, and then use IQ modulation to modulate an RF carrier and generate the modulated signal at RF. In terms of the software, how do you create those waveforms that go into the baseband generator? We could use a number of different things. We could use general programming languages like C++ or C#, something like that. We could use MATLAB, which is a very general purpose tool to create any type of waveform you might want to do. And then there are products like the Signal Studio software, which are very format specific. So if you want to create a WCDMA signal or GSM, you can do that, or wireless LAN signal. Again, that's a good tool for specific formats. All right, so our setup then might be something like this. If we wanted to record actual signals off the air, we could use a spectrum analyzer. For example, the PXA has 2 gigasamples of memory, which if you record at 160 megahertz of bandwidth, that gives you about 2.5 seconds of recording time. And then that can be played out through the signal generator, so that would give you probably the most realistic type of test signal for your jamming system because you're using actual recorded signals that might have been collected in the field. Then using the MATLAB software, we can download either the actual signal or a simulated signal into the signal generator and then play that out and exercise the jammer. All right, so those are some of the basic techniques that would be used. Again, with the amount of time we've got to talk about it here, I can't go into any big details, but if you'd like more information, certainly you can visit our website, and we have a lot of information on these kinds of techniques that can be used. And again, the whole idea here is to provide as realistic a scenario as we can to exercise the jamming equipment to make sure that it's operating properly before it's fielded. Okay, I think we're about out of time, but I just wanted to see if there's any questions any of you might have. Okay, thanks very much.